So, welcome. My name is Uberto, and we'll talk a bit about Kotlin and the game of Go. This want to be something fun and relaxed talk, so if you have any question, you can interrupt me or we can discuss later. I'll be around also tomorrow, so no problem. Before starting, my Twitter handler is Ramtop, the one on down. So if you like the talk, or maybe if you don't like the talk, we can interact via Twitter. But especially if you are interested and you want to contribute or you want to do something yourself, we can discuss. And okay, so my idea was basically I play a bit of Go. Go is this game, and the Go became very famous worldwide last year because Google did for the first time a computer program that was able to beat the world champion. And that was something that everybody thought was very, very still far in the future. And the last people were saying like 10 years in the future, but Google managed to do last year. And it did using deep learning and some other techniques. So then first Google, okay, there is a follow-up because first Google won the world champion, beat the world champion. And that will be more or less the middle one, AlphaGo Lee. Lee is the name of the world champion. And then Google did a version better. And then they did another version, AlphaGo Zero, which is still stronger because up till down, basically there was this deep learning when Google was taking all the matches of Go and feeding to the computer. The computer was finding the best moves. And we will see exactly what does it mean. But then it did AlphaGo Zero that basically says something that, okay, let's completely ignore all the existing matches and start from scratch. So it was a computer playing with another computer without any knowledge of a Go, playing each other, and then kind of figure out its own rules as it goes. And this is, at the end, it was still stronger than the strongest one. But of course, to do that, Google have to use some kind of 1,000 of years of a computer machine. They have a really, really big number of a computer. And in case you are interested in computer Go, these are a few links with software that you can. And there is also Lila Zero, which is a kind of open source clone of AlphaGo Zero. But since the code is not that difficult, but since they don't have the resource of Google, basically the idea is that everybody can download, run on its machine for a few hours, basically, and then kind of donate the result to Lila Zero result. There is a database that collects all the results, so Lila Zero can be stronger and stronger. But this talk, okay, is about Go, but it's also about Kotlin. And basically, I did this project that it's on GitHub, it's completely open source. It's a very, very small bot that can play Go. It's nice because it's already able to beat me, which is a kind of accomplishment, and but it's very, very easy. It's not like those other programs that I showed you before that really is quite complicated. This is very, very simple, and if you want to spend a few hours, you should already able to tweak or see how it works. It's very, very simple. And the idea is to keep it simple, to keep it didactic, but to improve as much as I can. And the idea of my program was this book that was basically, in discussing the deep learning in the game of Go. But my problem was that the book code was in Python, and Python is really, really slow. So, yeah, it was didactic as a book, but not really fun to play with. So I say, maybe this Python code could look better in Kotlin. And I started this project. And it actually does. So what I learned, and we will see exactly. I really like mutable, nullable types in Kotlin, but you have to discipline yourself and not use the double exclamation mark. And then using immutability. And also there is another trick of functional programming is called algebraic data types, then to avoid the ifs. And then modern optimization is all about memory. I mean, if you think that to optimize something you have to squeeze the CPU, you're outdated, because in the modern program mostly is about memory. Because JVM is so good at compile the CPU, I mean compile the code, that the bigger problem is locality of memory, misses caches, and garbage collection. But also, yeah, the other things are nice in Kotlin is coroutines that allow to avoid locks, and then Kotlin is really awesome. So just how many of you knows Kotlin? They have some exposure, yeah. And how many of you knows about the functional programming? Okay, maybe. So how many of you knows Kotlin but not functional programming? Okay, nobody. That was exactly this. Just a very quick time. Basically, the rules of the game of Go is just to surround. So if you surround completely the stone of the adversary, you can remove from the board. I don't want to deep too much. I mean, if it's a very interesting game, but you can study. And then there is some tricky part that basically the idea is that if you surround completely the enemy, the adversary, and for example, in the first scheme, if the black put the stone in the middle, basically can win completely. But in the second scheme, in the middle one, if white has two eyes, two places where he can put the stone, but he cannot put in either of them because it will be suicide. So basically that means that the black shape is unkillable, is alive. And the player goal is basically figure out how to make shapes that are alive and kill the adversary shapes. The last one is a shape that seems like alive, but is not really alive, because if a white fill C and B and C, then it can also fill A and kill. So it's called false eye. But okay, that's enough from. Okay, so just to understand the algorithm, we call stone is a single piece. Each turn someone put a stone, so you cannot move them each turn. And a string is a set of stones which are in contact, and the liberties are the free spaces around the string. And the first piece of code, this is the algorithm to capture a stone. Can you read it? Yeah, maybe. Well, the nice part is that the left side is a Python code from the book, and the right side is my first translation in Kotlin. And you can see that they are very, very similar. I mean, if it was Java, it will probably need much, much longer, or even C#. Kotlin basically allows to be as much as concise and precise as Python, but the advantage of Kotlin is that, of course, it's type and it's optimized, and it, of course, runs on the JVM. The other interesting bit of this code, of course, then I changed this code. If you check out the project now, is a bit different because I optimized. This was the Python version, and which is very, very object-oriented. But then we can do better with functional programming using the types. And just to speak about functional programming, a nice trick of Kotlin is that has this algebraic data types, which are basically some types that can work like a struct in C, so you can have one type or another type. And in this case, for example, to represent a move in the game, the move can be a normal move, like with a point, so you can say this is the position, or can be someone that pass, or can be someone that resign. And of course, in case of pass or in case of resign, there is no meaning of giving a position. There is no position to play. So the Python code has something like the class move has a flag is pass or is resign. And then if that flag is set, basically you have to ignore completely the point, because the point will be null. And but in Kotlin, we can do better than this. Because if we do the sealed class on the top, you can see sealed. That means that that class cannot be extended outside the same block, the same file. So this means that and then we can basically create 3 instances of that class. Well, 2 singleton, pass and resign, which are just a singleton because they don't have any information. I mean, pass is pass. There is no information attached. And instead, play is a data class, which is a construct in Python that basically creates a kind of Java beans, where immutable Java beans, where there is a field called point of a type point. And it derives from move. So basically, the class move are only 3 instantiation, 3 subtype. Well, 2 are singleton, because it's written with object, and 1 is the data class. And so that means that every time we have a move, something called move, we can verify if it's a move at the type play, we can use the point. Otherwise, we cannot access the point if it's a resign or pass. And that also means that we don't have to put a point as a nullable, because a point is a string. I mean, is not a nullable type. So every time we have a move of subtype play, we are sure that there will be a valid position. And this really simplifies the code. There will be much less if. Or the second example, for example, is a structure which is a kind of a tree. And in the tree, each node has a parent, as you know. But the root node, the node at the top of the tree, will be without parent. So we'll have a parent equal null. But if we put the parent with parent equal null, then we have to specify that parent can be nullable. So every time we get the parent, we have to check if it's null or not null. Instead, with the Kotlin, we can use the second example, a special singleton to mean the root. Actually, it's the root parent, to be precise. And so that means that for the root, parent will be root. But parent will be never null. So we just have to check if we are going up, that parent is different from root. And so this is all kind of small things, but putting together, Kotlin really allows us to write more concise code, less boilerplate, and less possibility of having bugs. Then another interesting question of the game of Go is that differently from chess, where basically you know who wins. I mean, whoever killed the king, the adversary king win. Instead, in Go, it's who surround more territory. But sometimes it's very harder to understand who is surrounding who. For example, in this case, in the left, the group on this with the C is alive, so that's counter for territory for black. But the group with the D is not alive because black can completely surround and kill. So that will also count for black. So in this case, black will be in advantage. But it's not really easy to understand this. There are some configurations where even masters can have a doubt, and they have to play to see exactly. So how can do the computer? Basically, what the computer does is to fill up. So it just try to fill up all the moves, possible moves, where there are only left eye with, single stone empty. And of course, you have to avoid to empty that. And then it just count. So basically, you have to continue play until everything is full. And to have a discontinuous play, basically, I just have some benchmark that basically just play randomly from an empty board, just put random stones until it fills completely. It's not meant to be important for the as an adversary, but it gives an idea of the board. And so basically, this is the timings that in the performance. And you can see that the first version basically was the version on the book, just a copy from the book. And then applying some rules, like trying to use immutable object instead of a mutable. It really improved performance a lot. Then the second one was basically to store the neighbor of each position, improve the algorithm, then having select move to return state. So basically, have a state immutable and just pass the state. So there is you have really to see the code, but just using immutability and functional paradigm, and also improving the code. I mean, now it's quite fast. It's really like 100 times faster than at the beginning. And this is how can we see how computer program can play Go. So basically, for each position, it started from a given position on the board, and then it tried to see if there is some kind of a promising node that we wanted to explore better. It selects one node and expand, so it's the expansion. And then basically what it does a simulation. So from that position, it just play random moves. And of course, playing random moves from both sides until the end of the game is not very meaningful. But statistically, if the position is slightly better for white or slightly better for black, and if you play a lot of these random moves, at the end, statistically, you have one side that tends to win more. Depends on the starting position. So basically, the idea is that this Monte Carlo search, it just play a lot of random play on the same position, and then see who is winning more. When I have a winner, basically, it will report the result, and it also reported the result to all the parents. So at the end of example, the result was 11-21, black and white probably. After it was 11-22 because white won And so basically we have to do the same things. And then, of course, the tree grows very, very big. And the final leaf nodes are probably not that much significant. But up the branches, the top branches, are kind of good. They have a good indication if the move is a good move or is a bad move. So what is really important to have a good program is to play a lot of these random moves. That's why I try to. And this is the implementation. And so the idea is that first is like the algorithm. First we select the node most promising. Then we simulate a random play. So that just play until the end. And we get a winner, one of the two. And then we propagate the result from the one node up to the root. And this is just the implementation of propagate result. Basically, just record the winner until the parent node is different from node. So when the node is root, the ADT that we saw before basically stop. And the same things to select the next node. Every time is basically avoid the node which are completely visited or terminal, like if the node is someone that we know. And then you try to select the next node. And you can also say that in Kotlin we can use tailrec to say that this function is recursive, but there will be no tail recursion. How many of you know? Who doesn't know what a tail recursion is? Okay, so the idea is that in Java, basically, if you do when you do a recursion of the of one function, it will put the result on a new stack on the frame. So if you do a recursion a lot of times, at the end of you will full all the stack, and then you have a Stack Overflow error. And if there are some, in this case, for example, we don't need to put the stack because the recursive call is the last call of the method. After that, it exits. So basically, what Kotlin does is it's called tail recursion. It drops the frame and then call it again, because it doesn't need to remember the previous state. So in this way, it can call itself as many times without consuming the stack trace, which is faster and safer because you don't have the exception. And to indicate to Kotlin that you want this, you put that tailrec modifier on the method. So if your method is not possible to be optimized, you have an error at runtime, at compile time. Now we have a problem. Okay, this is work, and it works well, no problem. But how can we make this running on multiple core? Because we have a strong PC now that with a lot of cores, and this is completely single thread. And we can see that the selector node must be something that is unique. I mean, you cannot select more nodes at the same time because you need to wait for a result. And the propagate result at the third point is also must be something protected because when you update the result, you cannot risk someone else is updating the result in the same time. There will be some, you are going to lose the data. Instead, the random play that is completely, because each random play is completely independent from each other. So what we want is keep the random play outside and have a synchronize on select and propagate result. Now, one way is to put basically some locks and synchronize and make sure that all the other thread, when someone enter in select node and propagate result, will be unique. But that is not really optimal, and it's also is very easy to make errors and then have a memory conflict at the runtime. What we can do with Kotlin instead is using the coroutines and the channels. And basically, it works like there was actors, like if you know akka, for example, in Scala. And what you can do, basically, you select a node, and then you have a channel to request, and you send basically, please someone do the calculation for this node. And then you have as many workers as you want, as your hardware is allowed to. And one of these will pick up your node. Every time a worker will finish his work, we'll put the result back in another channel, which is called a response. And the result will go back to update status. And update status will update all the record, all the winners. And then you go back to select node. Now, the nice part is that update status and select node doesn't have to, they can stay on the same thread. So if they stay on the same thread, that means that we don't need to use a concurrent mesh map. We don't need to put any locks because they are guaranteed to run on the same thread. Instead, the random play, which is the one that takes more time, we can split on as many threads, as many coroutines as we want. And of course, if we have, for example, this computer has 4 cores, so the maximum output is slightly more than 4, like 6. No. If I try to put with 100, it will calculate, but it's not as fast as I do with 4 or 6. Usually a little more than the number of threads. And you can say, okay, this seems quite complicated, but in reality it's very, very few lines of code. So the top is the preparation. So to prepare we need basically to create the channel at the beginning. And so we have a number of workers, which is 6 in our case. And then we create a channel with a capacity. The capacity is basically something is called a pushback in the reactive programming paradigm. So every time you save something, when the channel is full, so basically you are selecting new nodes, but if no one is able to pick up the new nodes, the channel is full, so it's blocking the thread that is pushing for new nodes until someone will. It's like a blocking queue, and it's not mandatory. You can decide to use the capacity or not using the capacity. And the response is it's the same, but for the responses. So basically, we have two channels that connect all the actors. And then for each worker, basically what we create, we call this function build rollout actor, which is the second function. And basically it's the one that for every time there is a message, it will consume the message and do a random play, and then put the response in the response channel. So if we ignore the debug level, it's really very, very few lines of code. That something that if you use Akka or Java, in Java you really have to write a lot of code to make sure all this plumbing is working. With Kotlin, it's very, very easy. And then at the end, this is the main thread, the one that basically launch. And it's just a while loop that check when the work channel is full. If it's not full, it basically selects a new node and sends the new node. When the response is not empty, it will pick up the new response and then propagate the result. And in this case, we can be sure that the select the next node and propagate result will never happen at the same time, because only this thread will use. And there will be only one thread. This is run only in one thread. And this is the result of performance. I mean, these are not exactly, but you can download the program and try yourself. But this is on my laptop. It's quite consistent. And if I run with a single thread, I have more or less 100,000 rollout per second. No, not per second, for 30 seconds. This is 30 seconds. If I use just the logs, if I put the logs on the top too, I have a slightly better result. And doing some log synchronize, I also managed to have a worse result than not having, worse result than a single thread. Logs are very, very tricky. Then I tried again using algorithm with no logs, like using concurrent hash map, and which is much better. But using this is about 250,000 rollout per second for 30 seconds. But using the worker is definitely better, because there is no logs, and concurrent hash map has also very complex code to manage that. Instead, we have using the channels. Basically, we avoid the problem completely, and the code is much easier to read. Because, for example, the code without no logs, it was working, but it was quite complicated, and it was very delicate. So, if in the future we're going to change something, I will probably break, because it was everything must be very, very delicate. Instead, with the channel and worker, the code is very, very easy. It's small and it's quite easy to understand. So that's definitely quality code. And the 1 million is without doing rollouts, just to check what is the maximum theoretical speed is about 1 million. Okay, so before going to the next step, I want to show you the current. So this is the code. One question that they ask me a lot is about if the coroutines are experimental. If you try they are marked as experimental. But they are experimental only in the sense that they may change the API. Probably they won't, because now. But when they roll out the coroutines, there was some feeling that API could change. They are not experimental in the sense that they are not really working. They are definitely working in production, ready and solid. So this is more or less how it looks like. I can choose a move. And then it will give me an answer. Okay, this is a bit boring because, and you can see the number of rollouts, and then, yeah, but I don't know. Yeah. I just that I don't want 30 seconds for move. I want 1 second for move. We want stuff quickly. With the 30 seconds with move, the game is quite interesting. With the 1 second for move, it's not that interesting. It's a bit stupid, but it's very quick. So it's just put a kind of and here you can see more or less the logs. Basically, it won 10,000 rollout, and then this is the possibility of winning for each move, and then its best continuation. Which again, in this case, they are not so I do some random move, and I also respond with some random moves. But you can see that now he's thinking to win about 60% of the time, having 60% probability to win. Any question on, since I have the code here, maybe? Yeah, this is Monte Carlo. And so this is the main Monte Carlo node class. And also this, I wanted to show you some. Yeah, basically here, when there is a move, I can check if the move is pass or resign or play, and in case it's play, I can use the pointer to do the actual move. Okay, this is just a translation because there are two different set of. To use a library, I have to translate the move in the library, but it's. This when constructing in Kotlin allows me to use those sealed class and split the type. Also because everything is in the class cannot be extended, the compiler can be sure that I also have calculated all the possible cases. Other questions? And and this is the main exploration tree. Basically, is the main Monte Carlo. And run blocking is basically when you start using coroutines, you have to use a run blocking that basically, okay, everything here will use coroutines and is blocking the main thread. Because of course, so you can do all your stuff from coroutine and then fetch the result. If you don't need the result right now, in this case I need the result, I need which is the next move. If instead it was completely asynchronous, instead of run blocking I can use launch. And then basically launch means that I launch the continuation and the coroutines, and then it will finish in its own time. But I cannot do anything. I don't have any result basically at the end of the launch. Instead, with run blocking, I have the result at the end. But of course, run blocking it also makes sense to use at the top level, because inside everything will be using coroutines. And at the end, you can basically call the cancel sealed one, but basically that is killing all the threads or the stuff that has been created. Instead, the main while is very simple. Just check that the time is not expired, and then run the micro batch, the one that we saw. And I wanted to show. Yeah, this is also interesting. If you basically, how can Kotlin knows about that we are inside the coroutine? Well, it knows basically because there is I wanted to show you some. Yeah, for example, this is there are some function that with the suspend. And suspend means that that function will run inside the coroutine. And then what is basically in low level is translating, is basically adding a new parameter to the function. And the new parameter is the context of the coroutine. So inside the function, I can call, for example, a method like wait. Yeah, well, I can call context. and context is the context of the coroutine, basically. So I can check exactly, for example, there was I want to show you something about the context. Yeah, coroutine context, yeah. Basically, from coroutine context, I can check, for example, I can cancel, or I can decide how many, because here I don't have, but I can specify a context at the beginning. And if I put a coroutine context, I can specify exactly how many threads, real threads of the CPU will be used for that coroutines, or I can have a smaller tuning, finer tuning. But to be able to access this context, also you can check if it's active. It must be a coroutine, and the coroutine basically have this suspend. Where it is suspend? Yeah, this suspend hidden in the parameter. Okay, so next level, what I'm writing now is the problem with the Monte Carlo research is that it is very good when there are few possibilities, like in the middle game, end of game, because it considers all the possible results, and it will see which are. But in some position, like at the opening, you can put a piece here, you can put a piece there, but if everything is empty, it's very hard to have to understand which is a good position, which is a bad position. Also, if you really need to run a huge number of rollout to have a difference. So to help this, basically, this is what Google, the AlphaGo team, got the main intuition. You train a neural network to understand which are the moves that can help you. So basically, you get all the moves of the play, then you see who is winning who won the play at the end, and then you kind of assume that, okay, if this was winning, this probably was a good move. Instead, for the adversary, we say, okay, I lost, so probably these are not such a good move. And this is used to backtrace the learning of the neural networks. When it's very time-consuming. It really needs a lot of resource. But when you have the neural networks with a good input, what can happen is that the neural networks can suggest this position probably is a good position, and then you can start doing the Monte Carlo research starting from that position. And this is incredibly improved the Monte Carlo tree valuation. On my side, I don't have the resource of Google, and I don't want to do a huge. So my idea is, since Lila Zero is completely open source, to try to use Lila Zero data in my Kakomo, in my software. So if you are interested, in the next month, there will be a version that uses this. And here, for example, you can see in the graph the Lila Zero stronger, basically how good is able to play, and is going up and up as much as people are accumulating games. So they are running games in their home PC and then update the result to Lila Zero website. And it's getting better and better. And now it's already the best open source no sponsored software. There is another one, very, very recent, like 2 or 3 weeks ago, that is from Facebook, but is very strong, but always playing Go. But yeah, I mean, Facebook also put some tens of thousands of CPU to train the neural network. And that's it. So, any question if you want to discuss more, or if you like something about Kotlin or about Go?
Is there a good support for data science in
Well, in Kotlin you can use everything that is already in Java, and deep learning for J is very good. And there is already some port in Kotlin, but it's very, very easy to just take a Java library. I use it in Kotlin as it were.
Are you using a GPU for your calculations or LLVM?
Yeah, I mean for the deep learning or for the Monte Carlo? Okay, so for the Monte Carlo, no, there is no GPU. It's just using the main CPU. For the deep learning, yes, because at the end it will use some engine like TensorFlow, which is used. Well, it's not strictly mandatory, but the times are really huge difference. So it is about 100 times difference between having a GPU or not. The good part is that since I'm most of the time is spent in training. So if you really need a GPU to train your neural network, but just to run the neural network is not so, I mean, with the GPU it's faster, but it's not a big issue if you don't have the GPU. Because you just have to get the input, put the input in the neural network and get one result. Instead for training, you have to do this millions of times and then back propagate the result. So the difference is really, really big.
Have you been trying to use the native Kotlin compiler in LLVM?
Yes. The native Kotlin is not faster than normal Kotlin. At least at the moment it's actually slower. It's very quick, so the startup time are immediate, really like a C program. But the main issue is that, of course, it has no Java library. So everything that came from Java at the moment is missing. So you don't have, for example, some collections which are not complicated by Kotlin. You don't have a Java date, for example, if you need a date. You cannot use any other library. So they are going to do this, but for the moment I cannot translate this. I just tried to implement. For other stuff, instead, Kotlin native is quite good. We have 1 minute. Are there any other question on any other topic about Kotlin? Okay, thank you very much.